Good morning, dear student. In today's lecture, we are very much interested into third practical of conductometry, that is the study of hydrolysis of aniline hydrochloride. So, let us discuss some theoretical parts regarding to this hydrolysis of aniline hydrochloride, and then we discuss the practical procedure uh, to determine the dissociation constant, that is to find out the hydrolysis constant. It's not dissociation constant. So it is hydrolysis constant for this aniline hydrochlorides. So let's discuss some theory regarding to this practical. That is when the salt of strong acids and weak base such as aniline hydrochloride is dissolved in water, hydrolysis is occur. So aniline hydrochloride, it is salt of strong acid and weak base. So C6H5 NH3 positive. So it is a salt of strong acid and weak base. When it undergo hydrolysis, means the addition of water. That is, what is hydrolysis? That is the cleavage of bond by addition of water is nothing but the hydrolysis. So this is the salt of strong acid, that is aniline hydrochloride. When dissolved in water, hydrolysis is occur, and the cation of the salt interact with the solvent to form conjugate base. So what you get in this reaction, that is, so reaction with water, it is a reversible reaction. So what you get here, we get C6H5 NH2, that is aniline, plus we get H3O positive. H3O positive. That is when the cations of the salt interact with solvent molecule to form conjugate base of the salt and conjugate base of the salt and conjugate acid of the solvent. Conjugate base, this is your conjugate base of the salt. This is your salt, aniline hydrochloride salt, conjugate base and conjugate acid of solvent. So this is your conjugate acid of solvent. If so, again, this is your alpha. Let us consider this is your alpha after hydrolysis of this salt of aniline hydrochloride. Alpha is there. Again, the water molecule is there. Okay, and then if you consider this is the dissociate, this is the hydrolyzed form, then the concentration of this salt, it is nothing but 1 minus alpha. So you should remember, that is, whenever we consider this is the hydrolyzed form, if you consider this is the alpha, that is degree of hydrolysis, we can consider alpha is the salt hydrolysis, and then the fraction remain, that is 1 minus alpha. If a fraction alpha of the salt is hydrolyzed, if the fraction alpha of the salt is hydrolyzed, then the hydrolysis constant of given, the hydrolysis constant kh is given by applying the Ostwald dilution law. So same as dissociation constant in previous practical we discussed for acetic acid, same is in this case we can find out the kh, that is hydrolysis constant, and the kh is given as, that is hydrolysis constant is given as C into alpha square 1 minus alpha, or we can write this as C into alpha square 1 minus alpha, or we can write this as alpha square upon V 1 minus alpha. So 1 upon V is nothing but your concentration. So we already discussed in previous practical, that is 1 upon V is nothing but your concentration. So we can write this as alpha square V 1 minus alpha, or we can write C into alpha square 1 minus alpha. So we know that this alpha, that is the fraction of the salt hydrolyzed, and the remaining 1 minus alpha is the, it is unhydrolyzed form. So we can, with the help of this Ostwald dilution law, we can easily find out this hydrolysis constant, that is kh, with this formula C into alpha square 1 minus alpha, or this is the formula, that is alpha square V 1 minus alpha. Let us consider the second important point regarding to this hydrolysis constant of this aniline hydrochloride, that. So the first point is that the salt of the strong acid, that is aniline hydrochloride C6H5NH3, undergo hydrolysis to give the base of conjugate acid, to get conjugate base of the salt and conjugate acid of the solvent. So again we discuss this reaction, that is C6H5NH3 positive. So it is a acid, and water, it is your base. So after hydrolysis, what happens? This base gives its conjugate acid, and the acid gives its conjugate base. So we get C6H5NH2. So acid gives its conjugate base, and the base gives its conjugate acid, that is H3O positive, conjugate acid. And by the formula KH, which is equal to C into alpha square 1 minus alpha, one can easily find out if the concentration is given. Then if you know the degree of hydrolysis, it is not degree of dissociation, degree of hydrolysis, one can easily find out the KH, that is hydrolysis constant. Let us discuss the remaining points regarding to this theoretical concept. When V is the volume in liter, so let us consider V is volume in liter. V is the volume in liter containing 1 gram equivalent, of the salt. V is the volume in liter containing 1 gram equivalent of the salt. Then the conductivity of a solution of the salt in which hydrolysis is occur. Keep in mind, that is V is the volume in liter containing 1 gram equivalent of the salt. Then the conductivity of a solution of the salt. So the conductivity of the solution of a solution of the salt, the conductivity of a solution of the salt, that is your C6H5NH3 positive, the conductivity of a solution of the salt in which hydrolysis has occurred, will be made partly of the conductivity due to the ions, will be made partly of the conductivity due to ions of the unhydrolyzed salt, and partly due to the conductivity of the ions produced by hydrolysis, and partly due to conductivity of the ions produced by hydrolysis. So what is this? So we already discussed the reaction and the hydrolysis constant equation. What it indicate? Let us consider once again. V is the volume in liter containing 1 gram equivalent of the salt, such as C6H5NH3 positive. The conductivity of a solution of the salt in which hydrolysis is occur will be made partly of the conductivity. So whatever the conductivity of that solution will made partly of the conductivity due to the ions of the unhydrolyzed salt, and partly due to the conductivity of the ion produced on hydrolysis. So whatever the conductivity of the solution is due to the unhydrolyzed form as well as the hydrolyzed form of that salt, that is the conductivity due to the ions of unhydrolyzed salt and partly due to the conductivity of the ions produced by hydrolysis. If, let us consider the next point, that is if the degree of hydrolysis is alpha, if alpha is your degree of hydrolysis, and lambda c is your the equivalent conductivity. Lambda c is your equivalent conductivity of the solution at a concentration C. So alpha is a degree of hydrolysis and lambda c is your equivalent conductivity of a solution at concentration C. Then the lambda c, that is equivalent conductivity of a solution at a concentration C, is given as 1 minus alpha into lambda dash c plus lambda double dash c. So what is this lambda c? It is the equivalent conductivity of the solution at concentration C. 1 minus alpha. Alpha is your degree of dissociation, degree of hydrolysis. What is this lambda dash c and lambda dash double dash c? That is lambda dash c is your equivalent conductivity of solution of unhydrolyzed salt. So equivalent conductivity of solution of unhydrolyzed salt at concentration C. So lambda dash c is the equivalent conductivity of solution of unhydrolyzed salt at concentration C, and lambda double dash c is the equivalent conductivity of hydrochloric acid solution at that concentration. Hydrochloric acid solution at the concentration C. So if alpha is the degree of hydrolysis and lambda c is the equivalent conductivity of the solution at concentration C, then lambda c can be easily calculated. That is equivalent conductivity at that concentration is given as 1 minus alpha into lambda dash c plus lambda double dash c, where lambda dash c is your equivalent conductivity of solution of unhydrolyzed salt at concentration C, and lambda double dash c is the equivalent conductivity of HCl solution at that concentration. Then if you consider rearrange this equation, so let us consider the rearranging this equation for the hydrolysis, degree of hydrolysis. Then we get, so what you get, that is if you rearrange this equation, then what you get, alpha which is equal to lambda c minus lambda dash c upon lambda double dash c minus lambda dash c. So if you know this degree of hydrolysis, then we can easily find the hydrolysis cost. That is lambda c is calculated from the conductivity measurement of the solution, that is aniline hydrochloride, and lambda dash c is the conductivity of the solution in which hydrolysis has been almost completely suppressed by the addition of excess aniline. So let us discuss what is this. That is lambda c. What is this lambda c? It is the conductivity of the solution at that concentration. Lambda dash c is the equivalent conductivity of the solution of unhydrolyzed salt at concentration C. Okay, so this is the conductivity of aniline hydrochloride in presence of water. Okay, lambda c is the equivalent conductivity of aniline hydrochloride in water, and this is the equivalent conductivity of aniline hydrochloride in aniline hydrochloride solution. So you have to prepare aniline hydrochloride solution in aniline hydrochloride. That is, you have to dissolve this aniline hydrochloride in this aniline hydrochloride. N by 32 aniline. It is not N by 32. It is not aniline hydrochloride. So you have to dissolve aniline hydrochloride in aniline. So you have to use aniline. So this is the difference. Lambda c is the equivalent conductivity due to hydrolysis. That is, aniline hydrochloride is dissolved in water, and whatever the conductivity is your lambda c. Lambda dash c is nothing but the equivalent conductivity of aniline hydrochloride in aniline. So in aniline, that is in unhydrolyzed salt. So in aniline it does not undergo hydrolysis. Unhydrolyze. This is your hydrolyze. So lambda C, hydrolyze, unhydrolyze. This is in your aniline. So you have to prepare the solution of aniline hydrochloride in aniline. In this you have to prepare in water. Lambda double dash C is your what? The equivalent conductivity of HCl. So with the help of this formula one can find out the degree of hydrolysis, and if we know the degree of hydrolysis one can easily find out the hydrolysis constant. So let us discuss the material which is required. So again we required the conductometer, then we required the material, we required the instrument, that is conductometer, then we required 0.01 normal KCl solution to find out the cell constant. Then we required N by 32 aniline, N by 32 aniline. Second, we required N by 32 aniline hydrochloride solution in water, N by 32 aniline hydrochloride in water, and we required N by 32 aniline hydrochloride in N by 32 aniline. So whenever we prepare N by 32 aniline hydrochloride in N by 32 aniline, it does not undergo hydrolysis, means that is the conductivity due to the unhydrolyzed aniline hydrochloride. And whenever we prepare aniline hydrochloride in water, it is due to the conductivity, that is due to the hydrolysis, that is lambda C minus lambda dash C. This is the difference, and lambda double dash C is nothing but your hydrolysis, the equivalent conductivity of hydrochloric acid solution. So we required conductometer 0.01 normal KCl to find out cell constant. N by 32 aniline solution we required. So N you have to consider it is 1 by 32. So you have to prepare this 1 by 32 aniline solution. Then you have to prepare N by 32, means 1 upon 32 concentration of aniline hydrochloride in water. And then you have to prepare N by 32 aniline hydrochloride, means 1 upon 32 aniline hydrochloride in this N by 32 aniline. So this is your undissociated. So whatever the conductivity is due to the undissociated, and whatever the conductivity due to the dissociated, means hydrolysis. After hydrolysis, so the first part is you have to find out the cell constant, and it is very simple. The next procedure is very simple. First you have to find out the cell constant. So we are very much familiar with this formula, cell constant, that is the specific conductivity of KCl solution, 0.01 normal KCl solution upon the conductivity of the observed conductivity of 0.01 normal KCl solution. So first find out the cell constant for 0.01 cell constant for this KCl solution. That is we can easily find out cell constant by this formula, that is specific conductivity of KCl solution divided by observed conductivity of KCl solution. Then the part second is very important. Part second, that is your determination of equivalent conductivity of aniline hydrochloride solution. Determination of equivalent conductivity of aniline hydrochloride solution. Aniline hydrochloride solution. Aniline hydrochloride solution. So it is where you have to prepare different concentration, that is you have to prepare N by 32, then you have to prepare N by 64, and then you have to prepare N by 128. So you just first prepare, that is you first prepare N by 32. So just prepare first, that is N by 32 aniline hydrochloride. I will use the short form AH, aniline hydrochloride in water. So first you have to prepare N by 32 aniline hydrochloride in water. Second, you have to prepare N by 32 aniline hydrochloride in N by 32 aniline, and we required N by 32 HCl solution. Wood's equivalent conductivity is given. So its equivalent conductivity means lambda double dash C is given, that is your 393. Okay, so you just measure the conductance of this solution, that is N by 32 aniline hydrochloride in water and N by 32 aniline hydrochloride in N by 32 aniline. N by 32 aniline hydrochloride in N by 32 aniline solution. This is your lambda C and this is your lambda dash C. So you have to find out this, and then after that you have to find out specific conductance. That is, we know that specific conductance is your cell constant into observed conductivity, and then you have to find out the equivalent conductance, and that is equivalent conductance having the formula, that is specific conductance into 1000 divided by concentration, or specific conductance into volume equivalent divided by concentration. Specific conductance into volume equivalent, it is not divided by concentration. So you have to just remember this formula, that is equivalent conductance is given as specific conductance into volume equivalent, and the volume equivalent is given in the observation table. The volume equivalent for this is given, that is for both this case is given, that is 32,000. So with the help of this we can easily find out the equivalent conductance, and if you know the equivalent conductance, and then we can easily find out the degree of dissociation, and then we can easily find the hydrolysis constant. So you just find out this value, and then after that you have to find out the value of specific conductance. So specific conductance, which is equal to cell constant into observed conductance. After that you have to find out the equivalent conductance, which is equal to the specific conductance into volume equivalent. The volume equivalent is given in book in observation table, so we can find out equivalent conductance. Then you have to find out the degree of hydrolysis, that is alpha. So already we discussed the formula of this alpha, and then you have to find out the hydrolysis constant, that is C into alpha square 1 minus alpha. Similarly you have to prepare N by 64 and N by 128, and then you have to find out this value, that is lambda C, lambda dash C, lambda C, lambda dash C, lambda C, lambda dash C for N by 32, N by 64, N by 128, and find out the hydrolysis constant. So this is all about the study of hydrolysis of aniline hydrochloride with the help of conductometer. In the next lecture we discuss the remaining practicals of our course. Thank you.